Alright class, we're going to look at a few problems from the homework. We'll kind of use 10 as kind of a warm-up, and then we'll get into 12 and possibly 13. So number 10, we're going to follow our advice and pick what's inside the parentheses as u. So u is equal to 5x to the fourth plus 3. du, which is always found just by taking the derivative of u. 5x to the fourth, the derivative of that is 20x cubed, and the plus 3 goes away. I also put a dx at the end. For more details on that dx, you can ask questions later about that. So if we're going to use what we just created here, u and du, and we're trying to rewrite everything in the original problem, the goal here is to make sure everything is accounted for. So I'm going to start with the easy stuff. The u is 5x to the fourth plus 3, so I can replace all of that with u. So that stuff is in parentheses, and it's being raised to the fifth power. So I can replace that part of the expression with u to the fifth. In this example, which again is one of the easier examples because what we have for du, 20x cubed dx, exactly matches up, 20x cubed dx exactly matches up with what's in the problem. So I can replace both of those things, 20x cubed dx, with what it equals, which is du. So this entire simple, complicated problem becomes a simple problem, u to the fifth du. So the antiderivative of u to the fifth is just equal to, we add 1 to the, this is a power rule, we add 1 to the power u to the sixth over 6. And our final answer comes from plugging in u back in. So instead of u to the sixth, we have 5x to the fourth plus 3 to the sixth over 6, and of course our plus c at the end. All right. Now that we're warmed up, let's try number 12. And this one, right off the bat, looks insane. Let's make it look slightly less insane by adding in some parentheses, because I know trig functions, are trig functions of something. So when I see all those things, it just makes it a little easier to do it that way. One other little thing I'm going to do, which will hopefully become apparent why I'm doing this in a minute, but this cosecant to the fourth, remember that I can rewrite that part of it as the whole thing to the fourth. And that's going to help me kind of think about this problem a little easier. It is crazy with the cosecants, but I think we can get through this. So, the main difference with this problem and the previous problem is that we're not just going to pick the thing in the parentheses to be u. So the question then becomes, how do we pick what's u? And I'm not going to get totally into the intricacies of how we pick u always. There is a method for that, which we can get into if you'd like. But one method is to look for something that's the derivative of another thing. I see cosecant, cotangent, and cosecant. And if I look at my handy-dandy derivative chart, I can see that negative cosecant cotangent is actually the derivative of cosecant. So what that tells me is I want to pick something cosecant to be my u. So what I'm going to do is I'm going to pick everything inside those kind of purpley parentheses I just drew, and I'm going to pick that to be my u. And believe it or not, that was the hardest part of the problem, picking u. Because after that, we're going to see that some cool things happen. Once I pick cosecant of negative 4x to be u, the du is a chain rule. I'm going to start with the outside. The derivative of cosecant, which I had on that chart a second ago, the derivative of cosecant is negative cosecant of negative 4x times cotangent of negative 4x. And because it's a chain rule, I need to multiply by the derivative of the inside. The derivative of the inside is just times negative 4. I can rewrite this a little bit. Bring the negative 4 out front, negative 4 and negative make a positive 4, cosecant negative 4x, cotangent negative 4x dx. So what happens here is u is the stuff in the blue that I circled. So if I'm trying to rewrite the original problem with u's now, what I can say is I can replace that entire piece in the parentheses here with u to the 4th power. I put it in pink before, so I'll just match that again. So I replaced all of that. And the cool thing is that 4 cosecant negative 4x, cotangent negative 4x exactly matches that stuff there. And the dx matches the dx there. So in other words, everything I just underlined can be replaced by the simple du, because du, the derivative of u, is just all of that stuff. So it looked like a really complicated expression, but once I picked u correctly, it became a very simple expression, because all this other stuff, all that other junk out in the front, was really just the derivative of the other thing. And that's why U-substitution works really well sometimes. The derivative, antiderivative of u to the 4th becomes u to the 5th over 5. Oops, I'm doing the antiderivative. I don't need to do that. So u to the 5th over 5, which if we plug u back in, we have cosecant of negative 4x. And I could put the whole thing in parentheses and raise it to the 5th power. I can also choose to put the 5th power right there as a little shortcut. Over 5 plus c, and that is our final answer. And, you know, I know I've been talking for a little while, but if you want to look at number 13 too, I have that waiting for me on the next page here. This is actually, I think, a slightly easier one than the previous one. It doesn't look as complicated. Our method of picking the thing in a parentheses that we've relied on so far does work on this one. So I'm going to pick everything in those parentheses to be u. So u is equal to 5 plus ln negative 5x. And if you want to draw some extra parentheses around that negative 5x to show that it's inside the logarithm, that's fine too. It helps me. The derivative of that, the derivative of 5 is just 0. I don't really need to write that, but I will for fun. The derivative of natural log is 1 over whatever's inside the parentheses. Because there's a function inside there, I need to multiply by the derivative of the inside too. The derivative of negative 5x is just negative 5. If I were to simplify this expression, the negative 5's cancel out, and I just end up with 1 over x dx. Now before I try to substitute this back in, I just want to point out one property. I see that the derivative is 1 over x, which I can see is kind of this whole thing over x here. So if it helps you to write this out, I'm going to rewrite the problem as, instead of the whole thing over x, I'm going to call it 1 over x times all of that stuff. 5 plus ln negative 5x all to the 4th dx. I forgot my dx. I always do that. So this is the same expression, just written with 1 over x out in the front. And the reason that helps me is I can see that my du, my 1 over x dx, is right here. It's 1 over x and dx. There's my two pieces that are both du. So when I rewrite my problem, I can replace both of those things with a simple du. And because we usually write that at the end, I'm going to leave a little space and write it there at the end. Everything else in the expression, all of that stuff except for the 4th power, is what I called u. So I can rewrite everything in the parentheses as u, and it's still to the 4th power. So again, we have something that looked really complicated that boils down to something not quite so complicated. The antiderivative of u to the 4th is u to the 5th power over 5. Again, adding 1 to the exponent, dividing by that exponent. And my final answer is just plugging in the value of u back in. 5 plus ln negative 5x. That's all to the 5th power, all over 5 plus c. And hopefully that will help you attempt the kind of matching problem. So 13, that should help you with number 14. And